Okay, we're here at go2math.com working some calculus, and we're doing some Newton's method. Newton's method, and I believe that's it. That's what we want to look at. All right. Whoa, we got a graph here. Okay, this is what's going on in this problem. So much like 1 and 2, we're doing the same thing except a little twist here. We've got two different functions. We've got an x squared minus 9 and a g of x, which equals to 6 of x. But we are going, you see where the graph right here is crossing? Do you see this where I should say the graph is intersecting? The orange line and the green line, these two graphs are intersecting now. The f of x is the green, and the g of x here is going to be the orange. And we want to find where it is the intersection. Now, actually, what we're going to find is the x coordinate, the x. We're not interested in the y, just the x. And what we're going to do is we're going to use Newton's method, believe it or not, to figure that out. Okay, we're going to use Newton's method. So it's it's pretty interesting actually. Um, the initial guess is at 6. And I don't know, let's read the problem here. Use Newton's method to approximate the x value of the indicated point of intersection of the two graphs. Continue until two successive approximations differ by less than 0.001. Now that's less than. That's not less than or equal to, that's less than. For functions, okay, we're going to round to 4 decimal places. Alright, so let's actually let me jot this down here real quick. And hopefully you're doing the same thing. We got x squared minus 9. And then we have g of x is equal to 6x. And our initial guess is going to be x naught equals 6. X naught is equal to 6. So let's move over to the board. Alright, and I guess what I'm going to do here is just kind of, we're going to, alright, so I just went ahead and kind of sketched out the graph here. So this is our f of x here. This is f of x. And then this one right here is going to be our g of x. And this is supposed to be a straight line here. It looks like I got kind of crooked. But anyway, this right here is what we want to approximate. And that's whatever this x is right here, where the two graphs are intersecting. Alright, where the two graphs are intersecting. And the way you do that is, it's actually pretty simple. We have f of x, go ahead and write both these guys, x squared minus 9, and then we have g of x is equal to 6x. Okay, so to find out where these two are intersecting, you would just set f of x equal to g of x when their two y values, right? When their two y values here are equal, and then we just solve for x in this equation. That's all you have to do. So let's come over here and do that. So we have x squared minus 9 is equal to 6x, and then we just solve for x. But what we're going to do is we're going to get this set up to where we can use Newton's method. X squared minus 6x minus 9, right? So we could use what could we do here? 3 and 3? I don't know. We could probably factor that. No, make quadratic equation, whatever. Safe to say. But we want to solve for x in this problem. Okay, want to solve for x. And what we're going to use is Newton's method. We're going to use Newton's method, and I'm going to write Newton's method down. It's x of n plus 1 is equal to x of n minus f of x of n over f prime of x of n. So hopefully you have worked problems 1 and 2, and this is doesn't look foreign to you. But we get this problem and we break it down to where we're here, and we want to solve for x. Well, we do that by using Newton's method, right? By using Newton's method. And now our initial guess, did I write that down? No, I didn't. X of naught is equal to, what did I say, 6? X of naught is equal to 6, yeah. All right. So it's pretty simple. What we're going to do, so X of naught, so X of naught plus 1 is technically what we're doing here. So this is X of naught, and it's 6 minus, and then we plug in f of 6, so we just plug in, and this is actually right here, I didn't state it, but that's going to be our f of x. Right now I'm using this f of x. Let's not get this confused. Let's not get this f here confused with this f, okay? These are two different f's. We've now defined a new function here, okay? We've now defined a new function, so be careful about that, all right? Okay, so we're going to take 6 and plug it into our new function, our new f, I guess I should say. And so this becomes 6 squared minus 6 times 6, then minus 9. And then that's all going to be over the derivative, which I didn't even find the derivative of that. I should have wrote that out. So the derivative of this is 2 times 6, and then minus 6. Right, that would be the derivative. So we want to get this number and round out to a bunch of decimal places. That'd be the best idea. So let's actually do that. And I found the best way to do this is just, cheap calculator. And anyway, okay, so we got 6 minus, or what I do on the calculator is I take answer, A and S, and I go minus 6 squared, or answer squared, minus 6, right, times answer. Remember, answer is equal to 6, and then minus 9. Oops, need a minus 9. Divide that by, we got the bottom stuff to deal with. 2 times answer minus 6. Got a lot of 6's going on in here. Okay. And I get 7.5, and that was it, actually, 7.5. Okay. So that's our x of 1. That's going to be our x of 1 there. And, okay, so our x of 2 is, I guess I could put equals here. So we take the 7.5 now, and we plug it in. 7.5 squared minus 6 times 7.5. Missed that, I had the bad cough. Minus 9 over, of course that's over 2 times 7.5. My gosh, minus 6. Alright, so we get that, and that is going to be 7.25. So x of 2, I should say approximately 7.25. I mean, that's actually exactly 7.25, but okay, now remember two successive approximations that differ by 0.001. We got 7.5, 7 point, so those don't differ. So now let's do x of 3, right? So 7.25 minus 7.25 squared minus 6 times 7.25 minus 9. And of course, that piece right there is all over 2 times 7.25 minus 6. So let's hit enter on that, or equals, whatever you want to do here, 7.24. Hope I don't run out of paper. What was x of 3? Oh, no. Yeah, I got confused on that. 7.24. So we're getting close here to two. It's got to be less than. Let's see, 7.24266. 7.24264. You know, you look at this, what do these differ by? Is it less than 0.001? Doesn't look like it. So now we do x of 4. I'm going to go ahead and let you, get the x of 4 there. See if you can figure that out. I got 7.2426. Okay, this looks like this is two successive ones. It's definitely going to be differing by 0.001. We want to get two successive iterations that differ by. So in other words, what I'm saying is x of 4 minus x of 3. Um, let's take their absolute value. Must be less than 0.001, their difference. And I believe that they are. Let's go over here. Okay. Oops. And I'm going to hit the answers. 2426, yeah. Just making sure. Right, and we got 4 iterations. You'll see a number right here come up, say 4 iterations, and I've gone over and over on the programming on that and had some issues with it. What did I say? 7.2, yeah, that was the 4th iteration there. 7.2426, that was the 4th iteration. 0.2426, okay. Alright, so that's all you have to do, okay? That's it. But what's really cool about this is, now I'm going to click this problem here to get a new graph to pop up. Let's click it again, get a better graph. What's really cool is we can approximate where these two graphs actually intersect using Newton's method. Okay, so if we have issues where we can't solve for x and solve for x, okay, it's beyond the quadratic formula. It's like to the 5th power or something terrible. But and we can't solve for x in the problem. We'll want to use Newton's method to find where these two graphs are intersecting. So that's one of the cool things that you can use with Newton's method. Anyway, one of the applications, I guess you could say. All right. Well, I think that's going to be it for Newton's method for a while. I think you got the idea of how to use Newton's method, and I shall see you here and talk to you later. All right. Bye.